me make sure this is working and we'll. So welcome everyone. So let's get started. So hopefully the second lecture of the semester will go a little bit smoother than the first one. Kind of in the room. I still need to figure out how to use this room appropriately. This is not a huge screen, but we got all these other screens around. So I'm hoping we'll figure out how to use the tables and some other stuff as we go. I'll kind of figure this out on the fly a bit. I am also recording on YouTube now. Let me go back to the web page. Linked off of this link, the YouTube should be a playlist for all the lectures. The first lecture I recorded, I forgot to share the screen, so you get to see me kind of waving my arms around, kind of in high resolution the whole time. So if you like that sort of thing, you can watch the video. This time I'm sharing the screen, so you'll be able to see the lecture notes that we put up on here. I've started updating the schedule and as we go. This V here now links to the video on YouTube, so you'll be able to kind of go there and find it. There's in addition to the playlist. So this will link to the slides that I used on the lecture on Monday. In the future, I will have these kind of these PDF notes. This will look like this, where it describes it. I've written something up in LaTeX, and then there'll be something inside the dot which will show what I wrote on the iPad. So you'll have all the stuff from the lecture. Again, I think it's really useful to be here, and we'll try and make the class more than just the lecture. So I think, you probably get maybe 80% of the lecture if you just watch it online and you watch it carefully and you're paying attention, which you probably won't be as much if you're online. So if you're not really paying attention, you're probably getting maybe 50% out of it. So I think, again, I want to encourage you all to come here. So we're right by a bunch of lunch spots, and then you can, come up here for class. Okay. The first homework assignment is now posted. This one is a kind of a short time window, but I kind of want to give you a flavor of what the homework assignments will be like and force you to start looking at it before the drop ad deadline. I try and get some stuff out there. So it's due in a week already. Usually this is not too busy of a time in the semester, but if you find it really too busy, I recognize it's a short time around period. So maybe ask me and I could push it back, but I wanted it to be due on a Wednesday to kind of fit our schedule. The homework, you can get to it if you if you click on here, you'll see the PDF on here. It's linked off of here. Then you'll turn it in through Gradescope. Instructions at the top. If you click on this link here, it will take you to a template inside of Overleaf. Okay. If you haven't who's used Overleaf before? Who's used LaTeX before? Has not ever used LaTeX before. Okay. It's a really good way to write in math and formalize stuff. A little bit of a learning curve. You don't have to do it. You can do something else so it's clear. People have done it in Word, but you have to upload a PDF into Gradescope. There's a template here. I don't know why it's not joining the project, but it's not one you can edit. You view only. So if you copy the project, once you see it, then you have a template for the homework assignment, and it shows you kind of how to do it. If you haven't used Overleaf before, it's an online kind of thing where you edit on the left and you see it compiled on the right. So it's pretty easy to use. So that's what I would recommend doing for the homework assignment. The stuff it'll be on will be basically what we cover in the lecture today. So after today's lecture, you should be ready to do for the content of the homework assignment. So that's why it's okay. It's due in a week. I don't think it should take you a week to do it. You'll be kind of running some simple experiments that we'll be talking about in class today, empirically plotting them, and then answering some questions about And then comparing the experiments to kind of analysis, where we do mathematical analysis. And you'll use both of these things to try and to check that you've done everything right. A lot of times you don't implement right the first time. This is non-common, and you use both. Does the plot look like I expect it to plot? Does it? And how do I know what I expect it to look like? Well, I'll use the mathematical analysis. So we'll discuss some of this today. I've asked you to plot up to some fairly large sizes of trials, a number of things, like this is 1,000,000 and 10,000. It may take a while to run this last part of the simulation in both of the two steps. Okay, so it won't take 10 seconds to run that last flight. It'll take more than that. That's expected. It should not take a day to run it. If it does, because your implementation, you don't have a programming background and your implementation is like super slow, you can run up to a smaller size, and you may not get 100%, but you'll get enough points on here. I just want to you kind of experience the growth of the runtime of these things. But it'll save you time to implement it in an efficient way in terms of the running of the algorithm. Okay, so if you take the time to think about how do I implement this well and fast, then you will save you time on the back end when you actually have to run it. It won't take you a day to run. It'll take you far less than a day. Okay. That seem okay? I guess you'll take a look at that, ask questions on Canvas if you have any, or me after class, and we'll figure it out. Okay, the next homework assignment won't be for a few weeks after that. Okay, sounds fine? Okay, good. You're still awake? Okay. All right. I want to also get a little feedback kind of on the AI policy for the class. I said you can use AI to help you do the programming and stuff. I want kind of the thinking part of it, where you have to answer questions. Did this work? How well did I think it worked? Mixing with analysis. Try and do that as much yourself as possible, but you can use AI to help you do it. I don't need you to learn the syntax from scratch on stuff, right? And on the project, I think I've loosened it up as well. I'm like, yeah, if you want to use AI to help you write the code for some stuff, and that accelerates what you can do, so you can do bigger and better projects, that seems good to me. But I want to get your feedback on all this. What do you guys think of that? How is this happening in your other courses?
On majority of the other courses, they basically just say don't copy and paste stuff into ChatGPT. So like if you have a homework assignment, like don't just copy the problem into ChatGPT and then just paste it back in. That's basically what they say, but you can still use it to, I guess, see stuff.
Yeah. Okay. Yep.
Most classes I've taken have been don't use it at all. But I had an AI course last semester, different school entirely, where it was like you can use it, but you have to specifically give a link to how you used it. It's like, what is the prompt you gave it? Make sure you're not copying and pasting. You have to submit that as well. You did this. I've only ever seen it that way or the other. There's no nonsense.
Yep. So with cheating things in the past, like one reason you guys don't like why other students don't like other students cheating is that it devalues your degree, right? If other students are getting A's and you're getting an A-, but you did everything yourself, you feel like, okay, that's not cool, right? With AI, it seems like, well, I mean, this is how people operate after they get out of school. They're going to go in the real world. They're going to use these tools. You're going to use them the way you use Stack Overflow to look stuff up, right? It's kind of a faster, better way to look stuff up, right? But I don't want you not to learn the material, but I don't want to put like weird burdens on you, like don't use spell check. Make sure you look everything up in the dictionary if you're not sure how it's spelled, right? So spell check is basically a form of AI as well, and it's not clear for me where to draw the line between these things. So does it seem okay with everyone? You're not like, you don't feel like it's devaluing it if other people are going crazy on AI, but you're learning. You're going to have to know it for the exams, and the homeworks are not worth too much of your grade. So, it's meant to be kind of a learning exercise for you. Yes, sounds good. Okay, this is similar. So other classes are more draconian or more bookkeeping kind of, you have to be more careful about it, or have they discussed it in the other courses? Yeah, they've discussed it. Is it similar or
I would say more strict.
more strict? More strict. Okay. Yeah. Yeah. I'd say, see, it's gonna get harder and harder to document it, right? Like put all the Google searches you put in during your assignment. That seems kind of like every time you looked at Stack Overflow, make sure you document it. That's okay. So that's why I'm trying to be loose. Okay, we'll see how it goes. I'll get feedback from you all later in the semester as well. But yeah, if you feel like it's not going well and this is too loose or something, and you should, I'd be glad to get feedback on this. We're as faculty, we're trying to figure out how to do this. So yeah.
There's a study and learn feature in ChatGPT now.
Okay.
Where
Yeah.
It doesn't just spit out the answer.
Okay.
It walks you through whatever process that you're doing.
Okay. So it's like the U-bot thing I talked about on.
But I don't know if it's free.
Oh, okay. Yeah. This U-bot thing, I know people, so I got a free trial for our course, but otherwise you pay like $1.50 per student or something. We'll see. So we're trialing it to see how useful it is. But maybe it's supposed to be tuned to my course, but I don't know. It didn't read my textbook or anything that I know about. So yeah. Okay. Great. So let's get into the lecture today. So we're going to talk about statistical phenomena, and let's see. I kind of the main thing I want to talk about today are the idea of having randomness in your data and how that affects the modeling. And we're going to walk through kind of very simple modeling, kind of like if you've seen that'll model things like the birthday paradox or the coupon collector's problem, if you've heard about those before. And this will be what you're doing on your homework. And we'll kind of talk about both the randomness in the data, and you start thinking about that and how that affects how uneven the data is. We'll see how you balance kind of what the empirical kind of things which you will do in your homework will compare to kind of how we would think of potentially mathematically analyzing this. We'll also think a little bit about the modeling underlying here. That's not just math and compute, but there's kind of, you have to choose, is this the right way to set up a model to run to the right abstraction to put math on top of, or to run simulations on top of. So how these things kind of are going to fit together. So okay, so we're going to be talking about kind of data. Is this too small? Data if it's too small, let me know and we'll adjust on these things. So we'll typically have a data set in the class. We'll be analyzing usually capital X. We'll think of this as X1, X2, up to Xn. Okay, and we'll say that these are going to be drawn from some often unknown distribution, going to have some parameters. Okay, we're not going to worry about the parameters today, but there's some distribution where it's drawn from, and we're going to say that the data is drawn IID. Okay, so that means, so what does IID mean? Who knows? Who's heard of this before? Yep. Yeah, so there are three things here. There's independent and identically distributed. Okay, this is kind of a broad assumption for much of data analysis. What it means is that every data point I draw, I'm observing, I'm making observations of the world is kind of what I'm modeling. There's some underlying distribution they're coming from. Every observation is independent of every other observation. And they're all identical. They're all coming from the same distribution. Okay, so my data, I assume, is all, each data point is independent, and they're all coming from the same distribution. This, when I was in your position, I had professors who said, okay, my data is IID, and I had no idea what it meant, and no one ever explained it to me, and you tried to type IID into Google, and it found some company with acronym IID, and I couldn't figure out what it meant for a few years, right? So I want to make this clear. This will kind of underlie a lot of the assumptions. Sometimes it'll be important that we model it this way. Other times it won't matter so much. Sometimes this is definitely the wrong model, okay? But this is what we'll be thinking about today. Okay, so we have data, and ultimately we'd like to understand something about the distribution from the data observations. And when you draw kind of, if you've taken a probability class or a statistics class, the main premise is the central limit theorem, which I'm going to state very generally as n goes to infinity, you can get better. So you can get better estimates. Okay. Okay. This is a very, very loose way of describing it, but this is the most important thing to take away from here. That as you collect more and more data from the same distribution, you can understand things about this distribution better. Okay. There's a formal sense about how the expected value that you're going to estimate is going to converge to the right, to the mean of the distribution, and it looks like a normal distribution and all this stuff. And there are lots of ways of making that formal. For now, we don't care so much about those. Okay. Okay, but the point is, if you get more data from the same distribution, you learn something about. This is the whole premise of data analysis, right? You gather data, there are observations, you should then be able to infer something about the world that these observations came from. Okay. Okay, so today we're going to have a very simple model. We're going to say that so that X will be a subset of what I will write as this square bracket M. Okay, this is going to be the set of 0, 1, 2, up to M minus 1. All the numbers, they're M numbers. You can count from 0 to M minus 1, or you can count from 1 to M. So it's not going to matter, okay? In fact, we don't care that it's these numbers. This is how computer scientists would index them. But they're going to be placeholders, an abstract placeholder for something else where there's a fixed universe, right? So it could be like examples could be these, could be IP addresses. Okay, so IP addresses, M is something like, is like 2 to the, was it like 16? No, it's like 10 to the 16, 2 to the
16.
Yeah, okay. I forget how many IP addresses there are, but there's a lot. I think 2 to 16 seems small, but there's a large number of IP addresses. I think it's 10 to the 16. How many IP addresses are there? But it's a large number, but it's fixed. Okay, so it's the fixed universe. And so a lot of the early kind of large data sets people were able to work with was like on having to do with the internet, where packets are being sent between IP addresses, and it's some large kind of fixed number, but it was fixed, so you could keep track, you could have a counter for each IP address. Well, actually, you couldn't, there were too many counters, but it's a fixed kind of universe here. Okay, it could also be the kind of words in the English language. About how many words are there, you think, in the English language? What do you think about how many words? How many words in the Wordle dictionary? What do you think about 10,000? Who thinks about 10,000 is right, or it's too small, too big? About 80,000 is closer. I like to say about 100,000 kind of is a good number for words in English. You can say just about everything. If you build, this is about the number of tokens that I think these large language models will use, about 100,000, right? And there may be 300,000 words that, like, if you are streaming all the things with spaces between them on Twitter, maybe you can get up to 300,000. Okay, but it's not everything. And if you just keep track of the top 100,000 words, this will be a pretty good representation of everything. The stuff you miss is probably going to be gibberish or in a different language or some long like it's a web address, like a link put into Twitter or into some article someplace. Spoken language is even smaller than this, maybe 10,000 or less, right? But you can keep track of, say, the top 100,000 words, okay? It could also be kind of people in the USA. Then M is going to be, was it like 360 million? Right, that's about right. So 300, maybe it's more than that now, but 360 million people, right? The US does a census every 10 years and tries to count every single person. And then I want to say, be able to kind of poll a random person, right? To understand something about the sentiment of the country. Well, I'm trying to ask one person out of 360 million people, every person here, right? And so I have some fixed, if the number of people is fixed, ignore kind of people being born and dying over time, but it's kind of a fixed number of people, say or it's smaller, the students enrolled at the University of Utah, then I can treat this as my kind of space of things. And so abstractly, I'm just going to use this between kind of 0 and m-1. Okay. And then we're going to add a distribution on top of it. We're going to say that the distribution is just going to be the uniform distribution on M. All right. So the probability that xi is equal to j is going to be equal to 1 over m if j is in M and 0 so otherwise. Okay, so as a uniform distribution, I'm just going to be randomly sampling people from the US in a poll. Hopefully, polls aren't able to actually do this. Picking a random word in English, this I can write down all the words, a random IP address, sending my packet to a random IP address. Okay, I want to keep track of what's going to happen. Okay, so this is the underlying model here. Okay, and so yeah, so okay, so if I were to implement this, you're going to have to implement where you are creating, you're going to implement this distribution. You're going to pick a random value between 0 and m-1. It could mean one of these things. How would you implement this?
What are you asking? How would we implement?
Yeah, I want to implement this distribution to actually generate samples so that are uniformly distributed. So I want to basically pick a random number between 0 and m-1. Okay, what would the RAM function do? What would I ask it to do? Yeah, actually, okay. This is two. This is I forget. It's not when I went to grad school back then. We had you can pick a random continuous value between 0 and 1. and that was the operation. Now you guys have much more powerful libraries. Okay, so you would just generate a random number between 0 and m minus 1, and that's a built-in function. Okay, so that was not the right question. Okay, go ahead.
Find the PMF.
Okay, we're not going to worry about we're going to not have to worry about the PMF. I chose this, so we don't have to worry about the probability mass function here. Okay, let me now rephrase the question. Let's say I have words in English, and I want to kind of every time I see a word, I want to identify it with one of these numbers. Or I have an IP address, I want to identify with one of these numbers, or a person I want to identify with one of these numbers. How would I set this up? Yep.
Well, you're gonna have to standardize the IP address, the words of the people, because you have different metrics.
Okay, I want to say everyone is associated with exactly one number. Like my number is 1,752,024, right? But everyone's associated with the number, right? So one way would be to build and store a database of all the people, and assign them with the number. But I may not have exactly the right number of people. I may not have this database. Later, there may be security reasons why I don't want to store this information, privacy reasons. If I have words in the English language, I would probably keep track of all the words. What I'm thinking of instead is I could use a hash function. Okay, and I'm adapting some of this lecture on the fly. This class used to have a lot more lectures on using hash functions and locality-sensitive hashing, so it was important for me to kind of spend more time on this, but I've kind of trimmed those out of the material a little bit because they're not as there's some better methods now. But what I want to mention for a hash function, like if you have a hash table, a hash function is kind of a map that goes from some sort of abstract universe, usually of strings, and this maps to some universe. So now I can think of my 0 to m minus 1 as an array, which I'm indexing into. And it's an array, and I can put, say, a counter in each cell of the array. So I can initialize the array as integers, and then I can count how many things I have everywhere in this array. And if this string is somehow a unique identifier for a person, or it's the IP address is already unique, or it's a word, and then I can map it into here without kind of worrying about storing this explicitly. I can let the hash function kind of do this for me without worrying too much about it. Also, if I get numbers, it'll map it to a random spot here, and this will be a way of kind of if I choose kind of my hash function h from a distribution of hash functions, this is how you would implement a hash function. You would choose a random one. Then this choice of the hash function is random, although this map is deterministic. So if the same IP address shows up twice, it always maps to the same location. Okay, so we want to think about one way of implementing this is to choose a random hash function, and then consider a bunch of to implement the algorithm of generating stuff from the distribution. I just put sequential numbers in the string, and it will hash them into random spots that are all going to be equally likely if this is a uniform hash function. Okay, so it should be that the probability, given that the hash function is from some database, or is from a family of hash functions, then the probability that the hash value of any fixed object X or a fixed string, let's call this a string equal to some J, is going to be equals to 1 over M if J is in M, and is going to be zero otherwise. Okay, so a uniform hash function, if I choose it randomly from the family of hash functions, is going to, for any string, have equal probability of being each of the j in this space. So this would be one way. Another way that this distribution that we're going to kind of study a bit today is going to arise. Okay, does this make sense? Have you seen, who's not seen a hash function before? Something like this. This is something you've seen in data structure course. This seems okay. All right, so this is another place that this is right. Yeah, question. No, you should always be I mean, well, so how would you choose a hash function? Good. This is what I'm going to talk about next. So, yeah. So how would you like to choose your hash function?
Whatever's built in.
Yeah. Okay. Good. So what I'm going to tell you is you should use built-in hash functions, but a built-in hash function, like from a hash library, is a deterministic function. Okay. So this is deterministic. Okay, so if I call this function, every time I call it with my name in there, it's going to get mapped to the same space, the same number, right? So I want this to be random. So how would I kind of make this, how would I implement something that's going to serve like to have this random probability here? Okay, and the key to that is going to be this A here. I wrote this A as this subset here. Okay, and this A is going to be the salt of the hash function. Okay, think of it could be like a random seed if you want to think about it that way. It'll work the same way. Okay, but this is going to be kind of a salt here. And so how I'd actually implement it if I just have one fixed hash function, and an example would be kind of like SHA-1, which is built in, okay, or SHA-256, whichever built-in hash function that you want is deterministic. Well, then what I would do to get the output, I'm going to get some value v as the output of my hash. I'm going to pass in string concatenated with the salt. Okay, so this will be the input that I'm hashing, and this will be the salt. And if I've concatenated these together, then if this A is chosen randomly or arbitrarily in a way that the hash function doesn't know about, then this output is going to act like this function here. Okay, so if you properly seed or salt your hash function, so it will effectively act randomly. If you use a built-in one, which you probably should, it's maybe a fun exercise to try and build your own, but you don't need to do that. Then you're going to, it's not going to be as efficient. These are optimized. They're pretty good. The SHA-1 and the SHA-256 hash family, they're built to be hard to invert. They come from early security work where they want this one-way function where it's easy and fast to compute one way, which is to compute the output of the hash. Okay, to this I can compute efficiently. Doing it the inverse, if I go from V and trying to figure out what this would have been, that's supposed to be hard. And if I change one little thing about the string, one thing in the salt, then it'll give me a completely different value V. I won't be able to infer anything from V about what's in the string here. Okay, and the effect of that is it looks and acts random for all intents and purposes. So this is a good kind of mechanism to use to kind of generate these things. You can also just generate random numbers in the assignment. That's using other built-in things. Okay, but this is another place where this kind of distribution will be arising. Okay, I again use built-in ones. Don't use modular hashing. This is some early implementations of computer science use this, and they encode patterns in there. I'm not even going to tell you what it is because maybe it's gone out of the zeitgeist, and I don't have to worry about you doing it anymore. But back when I was in school, people would implement hash functions themselves, and they would do it wrong, and it would lead to problems. And I've had to deal with some of these problems. So okay, okay. So let's talk about some statistical phenomena now. We'll start with the birthday paradox. Okay, and I don't know, when I first started teaching this course, usually people hadn't seen this before, but I'm guessing now probably you've heard of who's heard of the birthday paradox before? This is something you've heard about? Oh, okay, so not everyone is not everyone's kind of engaging. It's, but we'll see how that is. So what we want to set up here is that the number of days, the number of entries in that we can consider in the universe is going to be kind of unique kind of days of the year. Okay, so this would be kind of 365. We could think about that, right? So if someone asks you what your birthday is, there are probably 365 options of what you would say here. And so if we picked random kind of random people, what we want to ask is the probability that you have two people with the same birthday. So that means you're running this, you're picking random things, and you have a collision. You expect maybe I see everything eventually, but you're gonna maybe see collisions sooner than you would expect. All right. So we're gonna quickly simulate this in the room here. Okay, so I'm going to ask everyone for a birthday. You do not have to share your actual birthday if you don't want to, but fix the day in your mind now and don't change it. Okay. Okay. This is just for my bookkeeping here. Okay, so we'll go around the room and you're going to tell me a birthday.
June 26th.
June 26th.
May 8th.
May 8th. June 31. Oh, 21st.
August 9th.
August 9th.
April 30th.
April 30th. What? Okay.
August 16th.
August 16th.
November 17th.
November 17th. March 6th.
May 14th.
May 14th. May 28th. August 22nd. September 21st. September 15th. April 5th.
November 21st.
November, what?
November 24th.
November 24th. August 30th. March 19th. September 29th. August 29th. Okay.
August.
February 26th. August 15th. January 26th. July 10th. Uh-oh. September 11th. May 11th. Okay. January 12th. June 23rd. Jan 1st. Okay. August 24th. Okay. Okay, well, this this did not go as intended. Usually I've got a larger class that it's a safer bet that things will work, but this is not unexpected. I've run this with we've gone over 50 trials before with no intersections. This is this is more than you would expect to run before you would see a collision with two people with the same birthday. So yeah, okay. So who thought this was surprising that no one had the same birthday? It's kind of surprising. Who thought this is what I expected? Of course, no one's going to have the same birthday. Okay. And how many had no expectation? And how many didn't raise their hand for yes, no, or neither? Okay, a little better. Okay, finally, still about a third of you haven't raised your hand yet. Okay. Okay, so let's try and explain what we could have seen here. Usually with the classroom this big with people, and if you're not being adversarial on me, you didn't all get together before class and collude on this, then we would actually have expected, more likely than not, to have seen a collision with two people with the same birthday. Okay, so we didn't in this case, but it's also maybe, I would say, just ballparking about 10% of the time this would happen. So this isn't that unusual. Okay, so I thought that would get lucky, but this is not what happened. Okay, so if I ask, so let's look at the probability of a collision with K trials. So I have K people, so I'm going to do, or let's say N, because that's the number of data points we have, right? So we're drawing N random values. Probability of collision with N trials. Okay, so probability of collision with N equals 1. Probability of collision, if I ask one person, can that person have the same birthday as someone else in the set? No. Okay, so the 0. There's 0 probability one person has the same birthday as, yeah. Okay, so the probability of collision with N equals 2. This is going to be 1 over 365. Okay. What's the probability of collision with N equals 3? About, let's say, what is this? So 1 over 365 squared, that would go down. That would mean a smaller probability. No, it's going to be, what you want to say is the probability you have no collision. What's the probability of no collision? That would be kind of 1 minus 1 over 365. And how many pairs of people? If there are 3 people, that means there are 3 pairs. 3 choose 2. So if the 3 of you are together, 1 pair, 2 pair, and 3 pairs, right? So this is the probability of no collision is this, and the probability of collision is 1 minus this. Okay, see? So 1 minus 1 over 365, that 1 pair of people do not have the same birthday, and there are 3 pairs. Okay, so that's probability of a collision. So as the number of pairs increases, the probability of collision, of no collision, should go down, right? And then the probability of a collision should go up. Okay, so in general, if I follow this analysis for general N, I'm going to get 1 minus 1 over 365, the quantity N choose 2, right? And this is approximately N squared over 2. Okay, so this is, I think this is a pretty good analysis. Usually, it's not a perfect analysis. Okay, so let's talk about what's wrong with this analysis. What's good about this analysis and what's wrong. I'm going to say that what's good about this is that I can actually get a pretty good estimate of half the time if what I can say is if N equals 23. 23 is kind of the magic number. More than half the time, if you have 23 people or 24 people, you will get that. I say K equals 23, then I will plug this in. I will get something like this number is about 0.997, and n and see, and 23 choose 2. This is going to be equal to 253. Okay, and so then 1 minus 0.997 to the power 253. This is going to be approximately 0.532, which means that if I have 23 people, according to this analysis, about 53% of the time, 2 of them will share a birthday. Okay, so this, and with using this kind of modeling in mathematics, this generally works. If I have 23 people in the room and I run this experiment, then about half the time, 2 people will share a birthday, and half the time, everyone will have different birthdays. Okay, so this works really well, analysis for this sort of kind of understanding this concept. Okay, but there are multiple things wrong with what I did here. Okay, there's things a little bit wrong in kind of the mathematics. I didn't quite do the mathematics right. And there's also, okay, how did I model this problem? How did I get to here? That is wrong. Okay, actually, what I want you to do, I want to use these tables. I want to give you all kind of, let's say, 2 minutes to discuss on your table, and every table should come up with at least 3 things which is wrong about this analysis, and then we'll report. Okay, so all of you discuss with your table about this. Come up with three different things.
One of them is food is not more likely, but not really likely. I think all.
I don't think it goes. And I've done a lot of binomial distributions. I haven't never ended up with a square. So I don't think that's right. So that's mathematics on.
As long as that matters, you know, like people have special things in their life that,
Yeah.
so that's why it probably isn't.
I mean, but
So you have not.
So our argument is that there's other factors that are not being reported. We're speaking.
I don't get well, anniversary might be random. Christmas.
But then that would come down up to the person and whether they want to say that their anniversary is considered a birthday. How do we know?
Yeah, so great. So let's bring it back together. So I want people to report what are things that are wrong. What's wrong here? What's wrong with how we did this analysis? Okay. So I heard every table discuss this one. Okay, so birthdays are not uniform. Okay, how many of you know how non-uniform are they? Are they pretty non-uniform, or they're pretty close to uniform? There's a few more birthdays in like the fall, but it's like in like the 3rd digit of precision. So birthdays are pretty uniform throughout the year for the 365 days. Okay, fine. Okay, What's next?
Leap year.
Okay, leap year. Now it's getting a little bit interesting. Leap year. So M equals 365, 366, because there's Feb 29th. But now also this day deviates from uniform. Occurs roughly once every 4 years. So this one, so now also, so this is also not uniform. This one deviates a bit more, but it's 1 out of 366 days, so doesn't play too much of a factor. Again, this is, if I go this calculation, I got 0.997, it probably doesn't change the somewhere in there too much. Okay. Okay, what else is wrong? Yep.
On the I, well, say, 2 of those have the same birthday, maybe 3 of those have different probability. Now you go to N, there's 1, 2, 3, 4, 5. You have to add them, not do that.
Yeah.
Do that and you have to.
Great. So this step was already a little bit wrong, in fact. It's actually the first pair I check was 1 minus 1 out of 365. That was correct. But I only checked the second one if the first one did not have a collision. If the first one had a collision, then the probability the second one has a collision is actually going to be, or the second one will be, I think will be independent, but then the third one will be correlated. Because if the first two already intersected, then if the second one intersected the third one, then they all intersect. And so these probabilities get a little bit smaller every time I add a new check. So it's 1 out of 365, then I think it's 1 out of 364, and it's a more complicated formula here. When n is about 23, gives quite a good estimate still. But what's a way to easily see how this can go wrong if I use this for general n? Where's the choice of n where I can obviously see that this answer is incorrect? Well, let's do 0. Okay, let's do, if n equals 365, let's say ignoring leap years, what's going to happen? I'm going to plug it in here. I'm going to get 1 minus 1 over 365 to the power roughly n squared over 2. What value is that going to be if n is 365? It's almost 0, but the important thing is it's not 0, right? If n is 365, I have 365 people in the room and no one was born on a leap year, or 366 people in the room, right? Then there must be 2 that have the same birthday by the pigeonhole principle, right? There are only so many holes the pigeons can go into, and there must be a collision. But this analysis says that, well, it's a small but slightly positive number. So when n gets really big, this starts to fail. When n is about 23 or 40, like in this, roughly what this class is, then this is probably a pretty good estimate. Okay, so kind of the other one is the math. It's not, there's correlation in the pairs. Okay, so the pairs of people are correlated depending on if you're kind of conditioning on the previous people not having collided if you're checking the next person. Otherwise, you stop. If we would have run this and the first table would have had 2 people with the same birthday, we would have stopped the simulation. But if we are running the simulation going forward, then every pair was actually going to have a higher probability because I knew that there were more probabilities of a chance. But so there's a more complicated mathematical analysis here that can give me a better estimate as n gets very, very big. Okay. Again, for n medium size, this analysis still works. And so in this class, we'll sometimes analyze things approximately, not get the math exactly right, because we don't need to get the math exactly right. some of these other modeling concerns are about on the same order of magnitude as getting the math just right in the analysis here. And so we'll not do the deepest, most complicated analysis. Math, I'll give you things that give you the right intuition, and maybe I'll lie a little bit, but I'll tell you when I'm lying, and I'll kind of give you guidance on when the analysis is useful. Okay, other things that's wrong. We'll say have 3 for your table. Okay, is do you think our sample, here's another one, is the sample independent? So is the sample of your birthdays independent? I mean, assuming it was 40-ish random people, students from the U. So I would say maybe, but like I've had so I've had twins in the class before. Okay, so you can have twins which are more likely to be in the same classroom before, and they would share a birthday, and then the instance was not independent as before. Okay, if you're looking at, this probably doesn't apply here, but if you look at players who are in like professional hockey leagues, they tend to have more birthdays in the fall because the older, when they were older kids in school, they were bigger and got more conditioned to being kind of the big person in hockey. And the birth dates are skewed among like professional hockey players for this reason. So there are some populations where even the birthdays are skewed and not totally independent for other reasons as well. Right. Yep. It's also possible if they had a birthday. Yeah, a couple of people did tell me they would not be in class today. They said they were sick, but it might be their birthday. So I don't know. If it was my birthday, I'd want to be in class. So. Great. Okay. So this sort of way of thinking, and I would say most of this analysis is pretty minor, and kind of the way we estimated the probability of at n equals 23 gave a pretty good estimate here. Okay, but these sort of modeling issues, some of it is in the details of the math versus I was a little hand wavy in some parts of the math versus did I really have independence versus leap years, or kind of the birthdays are actually not uniform because of the data was not totally uniform for other reasons in the whole population. These are all things that we'll have to think about when we're modeling data. It doesn't exactly fit the perfect abstraction that we have. And that means maybe we don't have to do the math perfectly either. We can do approximations on the math. And we're kind of trying to get guidance to kind of understand if what we're seeing in the data is it really far off from what we expect, or is it kind of, okay, it's in the ballpark, I'm not surprised, I'm probably not doing anything wrong. The biggest thing I use analysis like for is to kind of determine if I've written code or my student has written code, and if something has gone wrong in the code because it doesn't look like I expected it to from some math and analysis and what I understand about this stuff. Okay, and so these sort of errors are probably not on the order that would affect these unless we got into very large N. And then the math is going to be a little bit broken. Great. Okay, so we talked about when do you expect to find collisions. Let me mention another problem that's related to this called the coupon collectors problem. And so this is doing something different. It's if I have a domain of size M domain. and I want to draw stuff uniformly at random from this domain, and I want to see all distinct kind of elements J in M. Okay, so I have a domain. Okay, and I'm going to see the first one, this one is repeated. This one is repeated. Oh. This one again. This one a third time. And then finally, I see this last one. So I see all the elements here. In fact, we ran a version of this in our simulation, and with the months of the year instead of the days of the year. And got a little cramped down here at the bottom. But I think we had no one in October or in December. Okay, so we did not see all the different months of the year here. They're not exactly equal probability. February has fewer days than other months, and 30, 31. But we didn't hit October or December here. Okay, so we had fewer days than we did not yet see all the months. How many trials do we need to do before we expect to see all of them? Right. So again, you don't. Oh, yeah. One more thing I want to say about this about where do we get, how many trials do we expect to see until? Yeah, I want to say one more thing about the birthday paradox. How many trials until we expect to have our first collision? Okay. When do we see the first collision? And I'll skip to the chase here. That's going to be when n is going to be roughly equal to square root of 2, or is it 2 square root m? Doesn't matter so much. So we expect to see when n is roughly 2 times square root of m, the number of things in the domain, then that's around when we're going to expect to see the first collision. Okay. And you can do it by playing with this equation and kind of trying to fix this to be a constant probability, about 0.5, and then trying to solve for n as a function of m, and you can kind of get this. Okay, I'm not gonna go into detail here, but approximately after roughly square root m of dates, you expect to see them. You expect to see the first collision. Okay, so which is kind of much less than a linear number. As the number of dates gets bigger, number of IP addresses gets bigger and bigger. I don't see almost all the IP addresses. Square root of the number of IP addresses is a much smaller number, right? That was, remember, 10 to the 16th, if that was number of IP addresses, then it would be 10 to the 8th is roughly square root of that. Okay, and that's a much, much smaller number. So you see collisions, even if they're uniformly random, much sooner than you are running into completion, where you see everything. Okay, so collisions are kind of a very natural part of the process. Coupon collectors is asking for when I see everything here. Okay, so how many trials do I need to do until I see everything, right? So what's kind of a guess for how many trials I'll need to do to see everything? It's going to be at least m, right? So say how many trials until we see all m, right? This originated from like in Happy Meals or stuff. You want to collect all the toys. And how many Happy Meals do you need to buy if they're M toys until you've collected all the toys, right around? Okay, assuming they're equally likely. Okay, so the answer should be clearly at least M trials. Okay, but probably more than that, right? There's going to be like 2M, like 2 to the M, M cubed, M squared. What do you think is the right answer? All right, who thinks it should be roughly 2 to the M or some constant times M? Okay, few hands. Who thinks should be M cubed? What, M squared? Okay, a few people M squared. 2 to the M, really big, bigger than like a big polynomial or exponential. Who thinks it should be something else? Okay. Something close to M. Okay. So we have options here. We have 2M. We had people say M squared, M cubed, 2 to the M, and then you said M log M, something like that, where pure scientists must be a log, right? Okay, that turns out it is the right answer. So it is roughly M log M is the answer here. It's a bit more than M, but it's only logarithmic factor more. Okay. So let's see how much. So maybe I'll give a little bit insight into it, and it's actually the expected value. That pink on red, not a good choice. Okay. The expected value is actually very close to this. So the expected number of trials is going to be is M plus some constant number, some weird number I will write down, plus the natural log of M, where this is 0.7, oh no, 0.577 dot. Okay, so people have resolved this very carefully. So it's very close to M log M, where the log is the natural log. Okay, the expected value number of trials. This one is better concentrated than the birthday paradox thing. Birthday paradox, I said roughly 10% of the time, where maybe we wouldn't see it with 40 people. Whereas this, the number of trials is pretty tightly concentrated around here. You can show like very strong convergence as M gets big. That's about M log M. Okay, and so the analysis here, let me just, we're doing okay on time, is that let's say I want to say the let's say then let me write down a clever way of framing this. Let Tj be the number of trials between the jth new coupon, the jth new thing we've seen, and the j plus 1th new coupon. Okay, so the Tj is an expected number of trials between the jth and the jth plus first new coupon that we've seen so far. Okay, so T0 is always going to equal 1 here, because that's between the 0th and the first new coupon. Every time I get something, it's new. I haven't seen anything else before. Okay? In general, what is the expected value of TJ? 1 over, roughly 1 over, and it's actually going to depend on J. That's kind of the clever way of writing this up here. How many, if I've already seen J coupons so far. So how many things do I have left? That means if T1 means that I have n minus m minus 1 coupons left I could see. So the probability of seeing it is m over m minus 1. In this case, the expected number of trials before this is going to be m divided by m minus j. Okay, so if j is 1, then m over m minus 1, this is slightly bigger than 1. Okay, if j is equal to m over 2, so I've seen half the coupon so far, okay, then the probability I get a new coupon is 1/2. So the expected number of trials is 2, right? So I would, let me just write this down, for j equals m over 2, then m minus j is equal to m minus m over 2 equals m over 2 equals 2, right? So if I've seen half the coupons, then I expect to do 2 trials before I get a new one. What happens when j is equal to m minus 1? If j is equal to m minus 1, then m minus 1 is equal to m. Okay? That means that there's only 1 coupon left to find, and almost every time I draw something, I'm drawing something I've seen before. I have to hit that one last spot. And so that becomes harder and harder as j gets bigger and bigger. Okay, so now I need to expected m trials in order to do this one. Okay, and so now I can write the total expected time. The total time is going to be the sum of j equals 0, or from 0 up to m minus 1 of tj. Okay, and so the expected value of t, the expected number of trials, is I can push the expectation through the sum because it's a linear operator, is the expected value of tj, and I know that that is equal to m over m minus j. Okay, and now I can factor out this factor m. That's a factor in everything. So I can write m equals sum j equals 0 up to m minus 1 of 1 over m minus j. And now we can look at the sum. I'm actually on this side, it's 1 over, if I instead sum from m minus 1 up down to 0, I can push this m inside of here. And oh, sorry, this is multiplied by. This is, I can rewrite this as m times j equals 1 up to m of 1 over j. Okay, m was this thing I factored out times the sum of 1 over j by kind of realizing that if I count from the top down, from the bottom up, it's a little bit easier to write and think about. And now this is a well-known quantity called the mth harmonic number. And it's known that the mth harmonic number is exactly this expression. Okay, so this quantity here, this is called HM. This is the mth harmonic number, and I know it's approximately equal to log m. Okay, so this is the analysis. This is how you get the expected value number of trials. Okay, so I did in class because it's a cute analysis to kind of see when you expect to see everything. Okay, now a lot of the caveats about how are these draws equally likely? Are they identically distributed? Did I model everything correctly? These also apply to this analysis, but if I actually want to use it. But this kind of gives you kind of some insight into where this bound is coming from. Oh, okay. So what did we learn today? Just to summarize. So we need to kind of to use math. We kind of need these simple models. Okay, once we have a simple model, then we can analyze it either approximately like we did with birthday paradox, or actually quite precisely like we did with the coupon collector. These models are wrong, but they're sometimes okay. Okay, and so we're going to live with some modeling error. We're going to try get into some sort of mathematical setting that we can actually use to kind of model the phenomena we're seeing. And this will be very different from this for the most of the rest of class. We'll start thinking about where data is coming from, and starting with the lecture tomorrow, or not tomorrow, on next week, Monday, we'll be talking about the very basic setting of how we can turn text into high-dimensional vectors. Okay, and so this will be, I will give you some concrete things that you can start using right away, and I'll connect this to kind of how modern stuff works and why it's still an okay, but not a perfect model to use. The other thing is that there are some kind of non-trivial phenomena. Okay, these can include these collisions that occur at roughly square root of 2m trials, and that when we kind of see all, this occurs roughly at m log m trials, right? So it's not, we don't see almost everything before we get a collision. We see collisions fairly early. And it takes an extra factor log m trials before we see everything. So this may not have been what you expected here. And so when we're saying, is this data normal? Is this unusual? We have to respect what the actual mathematics says. We can't say, oh, why am I not seeing everything yet? Well, you expect an extra log m factor trial. So an extra, factor 20 trials before you see everything. And if you see collisions or things that are really close to each other, that's not necessarily unusual to have these collisions. All right, so you shouldn't be surprised if things accidentally, if it's happening all the time and everything is paired together, then this becomes unusual, but just any collision is not. Okay, so when When we will later in the semester, we'll get to kind of anomaly detection part of the course, and we'll think about, we don't want to panic when we see a collision. We don't want to panic when we don't see everything too early. All right, so this will be kind of, we'll start to see some actual modeling with text and similarity search starting next week. And start looking at the homework assignment. If there are questions on it, please ask about it.
Do you upload these notes?
I will upload these notes. Yes.
I have a question. I skimmed through your book.